Hello, welcome to another exciting class on ExamPadi. Our topic today is magnetic fields, and in this lesson we will 1. Explain the concept of magnetic field. 2. Discuss carriers of electromagnetic fields. 3. Enumerate the types of magnets and how they are produced. 4. List the applications of magnets. 5. Describe Earth's magnetic field. And 6. Analyze the force moving around a charge in a magnetic field. Magnetic field is a region around a magnet where magnetic influence is experienced or felt. It is also a region where it exerts force on other magnets. It is a vector quantity. What are the properties of magnetic lines of force? 1. They originate from the North Pole and end in the South Pole. 2. Two magnetic lines of force do not cross each other. 3. Where the lines of forces are close together, the intensity of the field is greater. Where they are widely separated, the intensity is less. And when they are parallel, the intensity is uniform. Magnetic field intensity at a point in a magnetic field is defined as the force experienced per unit North Pole placed at that point. There are different magnetic field patterns. Let's take a look at few. 1. Field of a bar magnet as displayed in this image. 2. Attraction between unlike poles. 3. Repulsion between like poles. 4. Earth's magnetic field acts at a certain angle to the horizontal. The angle between the line of action of the Earth's magnetic field and the horizontal is called angle of dip, displayed in this image. 5. A neutral point NP is defined as a point at which the resultant magnetic flux density is 0. At this point, no magnetic influence is felt. Magnetic field in a straight current carrying conductor is due to different influences felt in the poles. Magnetic field in a straight current carrying conductor as displayed in this image. Let's take a look at different cases. Case 1. Two parallel current carrying conductors with current in opposite directions. Here, a repulsive force is created between the two conductors because the magnetic field moves towards the same direction. Hence, they tend to move away from each other. Case number 2. Two parallel currents carrying conductors with current in the same direction. Here, an attractive force is created between the two conductors because the magnetic field moves towards different directions. Hence, they tend to move towards each other. This is why you see sticks attached to the PHCN 240 volt lines in our streets, which prevents the conductors from moving towards each other. Let's take a look at a magnetic field due to current in a solenoid. A solenoid is a long insulated cylindrical coil. The field produced outside a solenoid is similar to that of the field produced by a bar magnet, but the field is straight in the middle of the solenoid. The end where the direction of the current appears anticlockwise behaves like the North Pole, while the end where the current's direction appears clockwise behaves like the South Pole. Magnets and magnetization. A magnet is a piece of material that can attract iron and other ferromagnetic material. Generators used in production of electrical power all depends on powerful and efficient magnets and magnetic materials. Properties of bar magnets includes 1. Direction. When a magnet is freely suspended, it comes to rest in the south-north direction of the Earth. 2. Attraction. A magnet has the ability to attract magnetic materials, e.g., steel, iron, and so on. 3. Force. A magnet exerts force on other magnets in such a manner that like poles repels and unlike poles attract. 4. The inseparable nature of poles on a magnet dipoles. If a magnet is broken into small pieces, however small it may be, it will still have a north and south poles. The smallest bit of a magnet is a dipole. 5. Magnetic lines of force originate from the North Pole and terminate at the South Pole. What are the methods of making magnets? 1. Electrical method. The best method of making magnets is to use the magnetic effect of an electric current. The material, a steel bar X, to be magnetized is placed inside a solenoid. Then the current is switched on for a few seconds and then switched off. When the bar is tested, it is found to be a magnet, as displayed in this image. 2. Single touch. The material X to be magnetized is placed on a table or a bench. The pole of a magnet Y is then dragged along X from one end to the other and lifted well away. It is brought back again to X at the far end, and the process is repeated several times, as seen in the image below. 3. Divided or double touch. The material X is stroked repeatedly in opposite direction by the opposite poles of the two bar magnets A and B. The stroking begins in the middle of X each time, as seen in this image. 4. Hammering in the Earth's field. A weak magnet could be made by using the influence of the Earth's magnetic field. This field acts at an angle to the horizontal called the angle of dip. It varies from place to place. It is about 70 degrees in England and Britain. If it is done in the N hemisphere, that is the northern hemisphere, the lower end will be N, and the same with southern hemisphere. Demagnetization. This is the process of making a magnet to lose its magnetic properties. It is the removal of the ferromagnetic properties of a body by desoldering the domain structure of that body. The methods of demagnetization includes hammering. Magnets can be partially demagnetized by hammering them hard when they are pointing east-west, that is 0 at 90 degrees to the Earth's magnetic field direction. The second method of demagnetization is heating. They can also be partially demagnetized by heating them strongly. And the last method of demagnetization is the electrical method. This is the best method of demagnetization. Here, alternating current is used. The bar magnet to be demagnetized is placed inside the solenoid with its axis pointing east-west. A rheostat is added to adjust the current value. The alternating current is switched on, and after a few seconds, the bar is slowly withdrawn from the solenoid to a far distance away, as seen in this image. What are the applications of electromagnets? An electromagnet is made up of a soft iron core around which an insulated wire is wound. It becomes a magnet only when current flows in the wire. It is a temporary magnet, and all temporary magnets are made of soft iron core. The strength of electromagnets increases with 1. Increase in the current within the coil. 2. Increase in the number of turns of wire of the coil. 3. Decrease in distance between the poles of the magnet. The applications or uses of electromagnets are as follows. 1. Electromagnets are used in cranes to lift heavy loads and objects made of magnetic materials like iron. 2. They are used in making electric devices like electric bells, magnetic relays, switches, telephones, earpieces, and so on. Let's take a look at the difference between temporary and permanent magnets. A temporary magnet comprises a soft iron core, while a permanent magnet is made of strong iron. A temporary magnet only becomes a magnet when current flows through it, but a permanent magnet still maintains its magnetic alignment structure even when there is no flow of current. A temporary magnet can be easily demagnetized, whereas a permanent magnet cannot be easily demagnetized. The Earth's magnetic field. When a magnetic needle or a bar magnet is freely suspended, it comes to rest roughly in the north-south poles of the Earth. This shows that the Earth acts like a magnet. Hence, the Earth must have a north-south poles near the geographical poles. The angle between the magnetic north and the geographical north directions at a place is called the angle of declination or variation, as seen in this image. The next is the angle of dip. This is the angle between the horizontal and resultant Earth's magnetic field. It can also be defined as the angle between the total intensity of the Earth's magnetic field and the horizontal, as displayed in this image. However, the angle of dip, declination, and Earth's horizontal phase strength are called magnetic elements. Let's describe the force on a moving charge in a magnetic field. The magnetic field exerts a force on a charge moving in the field because charges in motion constitute an electric current. For example, the motion of electrons along conducting wires. The strength of magnetic field, a vector quantity, is represented by B, called the flux density or magnetic induction. If theta is the angle between the magnetic field direction and the direction of motion of the charges, then the force F on the charge is given by F equals QVB sin theta. This force will be maximum when sin theta equals 1, that is, theta equals 90 degrees. The charge moves in a direction perpendicular to the magnetic field. This force will be 0 when theta equals 0, that is, the charge moves in the same direction as the magnetic field. Where F is the force in Newton, Q is the charge in coulombs, V is the average velocity of the charge in meter per second, B is the flux density or magnetic induction in Tesla. 1 Tesla equals 1 Weber per meter squared. Let's take a look at an example. Find the magnetic force experienced by an electron projected into a magnetic field of flux density 8 Tesla with a velocity of 4.0 times 10 raised to the power 6 meter per second and in the direction of 60 degrees. Solution. In the equation, F equals QVB sin theta. By substitution, F equals 1.6 times 10 raised to the power minus 19 multiplied by 4.0 times 10 raised to the power 6 multiplied by 8 multiplied by sine 60 degrees. Therefore, our force equals 4.43 times 10 raised to the power minus 12 Newton. Note, when an electron is projected perpendicular to the magnetic field, theta equals 90 degrees. That is sine theta, which is equals to sine 90. That would give us 1. Hence, F equals QVB when an electron is projected parallel to the magnetic field. If you would like to make a magnet on your own, try out these tips. We have come to the end of today's lesson. Here are a few questions to evaluate yourself. 1. Define a magnetic field and demagnetization. 2. Outline the uses of electromagnets and their applications. 3. Itemize the various ways of making magnets. 4. Distinguish between angle of dip and angle of declination as discussed in this lesson. 5. State the formula for calculating the force on a charge moving in a magnetic field. Thank you for learning about magnetic field with me. See you in our next video. Bye.